Not all yet. Now.
Hello, everybody. Thank you for coming out on such a cold, snowy day. I am delighted to introduce today's speaker. I'm Martha Palmer in the Computer Science Department and the Linguistics Department. And our speaker today is Professor Chen-Hao Tan, who is currently an associate professor at the University of Chicago in the Computer Science Department. He has a very illustrious career. He did his PhD at Cornell and then did a postdoc at the University of Washington, and then spent how many years?
3.5.
3.5 years here at the University of Colorado before moving to Chicago. He likes cold weather. He didn't get enough of it here. He is interested in human-centered computing, natural language processing, and computational social science, and has been very successful in getting, really, you're going to do that to me now, okay? Getting research funding, and I have to look this up because I can't read. The list is too long for me to be able to remember it. But in addition to an NSF Career Award and a Sloan Research Fellowship, an NSF CRII Award, and a Google Research Scholar Award, he also has research awards from Amazon, IBM, JP Morgan, Salesforce, a Facebook Fellowship, and a Yahoo Key Scientific Challenges Award. So we can't wait to hear about all this exciting research.
Great, thank you. Thank Martha for a very nice introduction, and it's very nice to be home. And I was walking from the parking lot to my old office this morning. It certainly feels like homecoming in many ways. And I actually had a few meetings in my old office. Anyway, without getting too much into nostalgia, today I'm going to talk about alignment beyond human preferences and using human goals to guide AI towards complementary AI. And as Martha said, most of my work is at the intersection of human AI. So that's what this talk is about as well. To start with, I guess I kind of want to start with this essay from Daryl Amadei, like the CEO of Anthropic. I think this essay is quite long. I think it's actually worth reading if you haven't got a chance. It's called Machines of Laughing Grace. And if you know, like Anthropic is more like this safety company within large language model startups, and its main message is about like not how do we prevent AI from being evil. But in this essay, it's actually more about the positive potential of AI. And here are some goals that was listed in this article that imagine if we have powerful AI, there's a terminology in this article instead of the typical AGI. When we have powerful AI, then we can potentially have amazing scientific discovery, potentially have the potential of curing cancer, solve poverty, I guess, improving democracy, and achieve peace and governance. And these are kind of amazing goals that we can potentially have if we have achieved success in AI. And on the other hand, I guess, like just as I was saying about the main identity of Anthropic, there's also a lot of conversation about AI safety and about the potential that AI will replace humanity, or like AI will somehow control all of us, and essentially achieving this more kind of matrix-style theme generation where all of us are in these batteries and AI is in charge of all of us. And because of these reasons, all these concerns, I think AI alignment is becoming kind of an emergent area. I guess it's pretty big already in many ways. But at the same time, I think the term alignment is also very much abused. So I'm going to try to define alignment a little bit using kind of some existing sources, and at least like at the end, honestly, I think I'm also abusing the word alignment, but hopefully I will define a version of alignment that is consistent with my work, and I think it has a lot of has some interesting perspective to contribute to this conversation. So this is Wikipedia's version of AI alignment. I think this definition is actually good. It's very broad, and what I'm going to use is certainly falls into this statement. AI alignment aims to steer AI systems towards a person or group's intended goals, preferences, or ethical principles. And then this version, I think this version can really drove a lot of actual work in this space. Comes from OpenAI. It says that our alignment research aims to make artificial general intelligence, so AGI kind of showed up, aligned with human values and follow human intent. And is this version that, like, it may on the surface looks very similar, but the second version certainly have a very clear instruction following flavor, and that's kind of has been driving the current research on current AI. Like, I think a lot of current AI is mostly follows this recipe where you first pre-train large language model, and this model will be seen as unaligned. And then you go through 2 steps to align this model so that it can follow human instructions. And sometimes people bundle together value or other things along with that. But what drives this process are 2 steps. One is supervised fine-tuning, and it mostly includes some supervised data, have some example input and example output. And then a big part is human preferences. Then it will do reinforcement learning from human feedback. And these human preferences will play a central role in driving this model in being more human-like. And that's kind of another implicit claim in this. If you make AI more human-like, then it will also comply to human values better. And if anything, I'm going to introduce a metaphor around AI, and this is the main thing, the main message I want to deliver in this talk. And this has been guiding a lot of kind of recent work in my group in thinking about how to navigate this space. And if we think about metaphors, then one useful metaphor that I think about this is to use these puzzle pieces. And I know some audience members related puzzles. Maybe this would be useful for thinking about. And after pre-training, we get a kind of these 2 sides. On the left, we get AI, and on the right, we get these humans. And what I want to deliver with this visual metaphor is that human intelligence and AI intelligence are of very different types. Like, these are very clear from their process. Like AI, we get the current version of AI by going through a big amount of data and just mostly trying to predict the next token. And that's not how humans obtain their intelligence. And we never perform, at least I have never really performed next token prediction in my life as a human. But I achieved a certain level of intelligence colloquially. And more important, and the second important part is that neither is perfect. And this human have their own biases, and there has been a lot of work showing AI has all kinds of problems. But the process of RLHF and SFT, or learning from human preferences, if we use human preferences to make human AI-like, in this metaphor, essentially we are trying to cut this circle side of AI, like this AI coming from planet circle into someone coming from this planet square. And that process, this process also can be reviewed by these typical benchmarks. For instance, this benchmark comes from Europe last year, and this is the title is kind of a man to web, a generalist agent for the web. And here are some example tasks. These are tasks that we typically perform. For instance, find one-way flights from New York to Toronto. And so I'm not going to enumerate all the tasks here. And these are not necessarily tasks that, first, they are kind of quite different from these goals that we had in mind earlier. And this is just illustration, a lot of these instructions data or these preferences data we give to these models are nothing really close to solving cancer or solving democracy or any of the goals that we talked about earlier. And I will return to that more later. And more importantly, this process also kind of introduced a lot of problems that we don't know, the process of trying to get AI into human shape also introduced new kinks that we didn't expect. For example, this recent article shows that this RHF process actually makes AI harder, it makes people perceive AI as better, people think AI's performance is getting better, but in fact, the AI performance actually drops a little bit. So as a result, it's harder for humans to know whether AI is correct or not after this RHF process. So what I'm proposing with this metaphor is to think differently, and I guess that's where the word complementary AI comes in, is that we have some notion of human goals, and we look at these human goals and see that the current human may be different from these human goals, and we think about how we can fill in that missing piece. So just to make this concrete, the human goals can be what we talked about earlier: scientific discovery, curing cancer, poverty, democracy, peace, and governance. Very clearly, I won't solve all of these in this talk, not even close. But I do think it's useful to have these goals in mind, and then think about what is the missing piece in the current version of human intelligence, and knowing that human intelligence is not perfect, and how can we build AI to fill in this puzzle piece and get this complete picture and achieve these human goals. So these are kind of the main story that I want to share in this talk. So I think it's important to have the human goals in mind when we think about AI, and using human goals instead of human intelligence to guide the development of AI. And then follow-up of this is that a corollary of this is that there are no universally desirable properties. Like, for instance, a lot of times we talk about hallucination as a bad thing. Like, how can this model hallucinate? That's a terrible thing, and it can trick people. It makes these models untrustworthy. But that might be the most important property for certain goals, which we will see very soon. And secondly, human preferences are not sufficient. So if we just use human preferences, we are really trying to use human as an upper bound. We try to get AI to be as similar as a human as possible. We don't know what humans cannot really do. Like, for instance, like certain human biases in hiring will also show up in that process. And as a result, AI will inherit those biases and won't be able to help us achieve better hiring outcomes in that process. So I'm going to kind of use two examples to illustrate this. The first one is hypothesis generation. This is kind of very recent work. You can see both articles were just last year. And I think this is a very exciting direction that I'm spending more time on. We actually just had a 2-hour brainstorming session on this topic yesterday. So I think it's very rich. We are just really scratching the surface. I'm very excited about this because like hypotheses are really important in scientific progress. Like new theories drive scientific progress. And I'm going to start with some very grand theories, but I will scale down very quickly given our kind of work so far. Like, for instance, like general theory of relativity, or Einstein is kind of one of the most celebrated scientists. And one of the prediction of this theory has driven scientists' work for so long. As a result, after more than 100 years, we only discover gravitational waves, which is one of the entailment coming from the original theory of relativity. Another very recent example, just within the context of large language model, is scaling law. Scaling law is this idea that the loss will keep going down as you make the model bigger in the next token prediction task that we're talking about, right? Like, this is a pretty much empirical statement, and this area is so active, we don't even know whether this is true or not. But so many companies are willing to bet on it, so they spend a lot of resources, and that's why we have so many different models. Like, we have OpenAI, we have Gemini, we have Meta, or Llama from Meta, and Cloud from Anthropic. All these models, each of them can take billions to train, because some people believed in this theory of scaling law, which is not even right. Like, likely is not completely right, but is good enough that people are willing to bet billions on it. Despite the important role of hypotheses, we actually don't learn about hypothesis generation as scientists. Like, most papers, like if you read the papers, they already present a hypothesis. They may spend a couple of paragraphs introducing related work and just kind of make up a nice story about the hypothesis. But most of the paper is about validating the hypothesis. We learn about how to design experiment. We learn how to run statistical analysis. We learn how to kind of design control for confounders. All of those learning is about validating hypotheses. We very rarely, at least personally, I've never taken a course that teaches me how to generate the hypothesis. And as a result, where do hypotheses come from? I think this image, at least this is my personal experience. This is really like how I generate the hypothesis. I just bang my head against the wall as many times as I need, and that's how I kind of try to come up with new ideas for next day. Just to get more serious, like I think like here are typical things, right? Read the literature, explore data, but fundamentally the real strategy is just think. And as a result, like we celebrate these kind of stories, right? Like in this case of discovery of benzorin, like I think this is actually true, and I will show an article on this. The story would be like this scientist actually dreamed this structure in his dream, and as a result, he came up with this idea. And there are follow-up with papers that just studies how Kekuri dreams up this structure. That's how kind of hard hypothesis generation can be. And I think this is kind of a good example where this is a critical step or critical task in scientific discovery, which is the overall goal that we want to achieve. And it's very hard for humans, and we don't really have like easy ways to go about with this, and AI can potentially help with this, at least to fill in some of the gap here in the process of scientific discovery. Just to make this more concrete, and this is when things will scale down very quickly. Like at least my work is not close to discovering theory of relativity yet, but hopefully we are making small steps towards that. Here is a very concrete example. This task that we are doing is AI-GC detection. AI-GC detection refers to AI-generated content detection. So here is a paragraph. And I'm going to ask you, just to keep you awake, whether this is generated by human or AI. Hopefully it's not hard. I'll let you read maybe for like, if I read it, I think that just made it maybe a little too easy. So I'm not going to read it. I'll let you read it for 30 seconds. Then ask you whether this is generated by AI or human. All right, I think it's about time. Raise your hand if you think this was generated by a human. Raise your hand if you think these are generated by AI. It's maybe about even. Like I guess this is indeed a hard task. Actually, but again, this is a good. I changed this. I think I gave like this example once in another talk. That audience got that example right mostly, so I changed the examples. That also probably made it harder. Anyway. The right answer is AI. For those people who answered AI, how did you determine the AI? Like, what were your reasons to believe that is AI? Like, Chloe, go ahead.
Like, you can think of after our comma, there's a lot of uncertainty in what thought is going to come next.
Wow, that's a very cool. Like, I guess, like, just as an example, that is what I mean by hypothesis. Like, I guess, like, maybe a natural way of using comma to organize parallel phrase structures. I guess I'm not sure even I'm saying that linguistically correctly. Anyway, any other hypothesis? Maybe we can get one and see whether, like, there are some like better hypothesis that is simpler, that is actually more reliable. But I'm not sure whether our AI came up with that hypothesis. I need to check. But go ahead.
Second sentence really seems a little unnatural. Like maybe not incorrect, but I feel like a person wouldn't write like that, but because it's technically grammatically correct, and AI wouldn't reject a sentence like that.
Cool. I think that is getting kind of somewhat close. But anyway, I think here are some example hypotheses, and later I will show even better hypotheses. But like this is a very good example. This is an illustration of like how you can try to come up with a hypothesis by seeing these examples. These are some example hypotheses that I came up with. And later I will compare this with what some of the AI come up with in a few slides. So these are like, for instance, like you can think of like maybe AI is more likely to use first-person pronouns. Maybe AI has more consistent sentence structures. Maybe human reading systems are more likely to use informal language, and so on. But this whole thing that what I'm doing, it has no factual grounds. Like this, or like what I'm doing is actually hallucinating. I'm just trying to be creative. I'm trying to think of what is possible. And as a result, this is a good illustration. Like hallucination is perfect for this goal. And in fact, most of scientific hypotheses, by definition, they are not valid before you run experiments or run a lot of things to validate it's true. And by most definition of hallucination, they would be hallucination because existing text corpora do not support it. So that's kind of our plan, and we are going to leverage the ability of large language models to hallucinate to see whether we can actually come up with good hypotheses to explain certain phenomena. Just to make this a little more formalized, even without equation. So the input is roughly you have a problem of interest. For instance, like what characterize AI-generated content in this example, and we have some data. And we can also potentially have related literature that can be helpful. And then our output is to generate natural language hypotheses that answer the problem of interest. And there are two possible approaches that was kind of alluded to in the example, in the input. One is that we can look at the data and we can look for patterns in data. And So the advantage of this is this is grounded in real data, but at the same time, you may potentially overfit. It's not really supported by any theory. But and on the other hand, you can be more theory-driven. You look at existing theories in the literature, and these are the results. You use the existing human knowledge, but the main downside is that you are also limited by human knowledge. It's unclear human knowledge is actually correct on some of these problems. And we will kind of, in this latest work, we are mostly combining these two, so I will focus on this latest work. But one of the components is the first data-driven work that I was reading, we first worked on. So in this data-driven work, this is kind of the rough idea. If you are familiar with multi-arm bandit, is one instance of that, but it has some interesting twists that may be of interest to like more theory-driven people. The rough idea is that we have these examples similar to the process we just went through. We will get the model to see some initial examples, then it will generate some hypothesis that becomes our hypothesis bank. And with this hypothesis, then we are going to see new examples and essentially like a multi-arm bandit system, each hypothesis will be an arm. We will pull that arm and see whether that hypothesis can actually support a correct prediction, and then update a award for each of these arms. And so we use this UCB style, our confidence bound style kind of reward update to update the data of each, update the reward for each hypothesis. And if the prediction is wrong, we are going to add them to this wrong hypothesis example bank. And then when we have enough wrong examples, we are going to generate new hypotheses based on these wrong examples. So the main intuition is that we are using these data labels as a guide to guide these hallucinations. So we not only have LLM, we also have this data that LLM can use to limit its potential generation space so that it generates better hypotheses as it sees more data. The main trick compared to typical multi-arm bandit, typically you have fixed arms. And in this case, because of the LM, we can always create new arms on the fly. So as a result, you kind of break the typical assumptions. Like there are some infinite multi-arm bandit paper, but in those cases, you have like fixed arm potential set. But in this case, LMs can potentially change your hypothesis distribution completely every time. But I guess if you assume your arm are all possible statements, then that is a possible way to fit this into existing theory, but that seems a very bad model of how these hypotheses are generated. And then the second part of this is to combine this with literature. The literature part is somewhat similar to retrieval augmented generation. So we try to search for relevant literature, then we summarize the key findings, then we use the key findings to generate a hypothesis. And one interesting that we did in this work is like, in addition to just get this hypothesis from literature, generated directly, we have like this, maybe these days you would call this agentic approach, where we have some examples, then we'll generate some hypotheses, then we will see the literature and then refine those hypotheses based on the literature. Then we go back and forth multiple rounds, and as a result, we get this kind of refined hypothesis. We call this set of hypotheses hyper-refined. And the original one was called hypogenic. And this will be kind of terminologies that will show up in tables. And they are only relevant for one particular kind of very interesting point related to AI GC that I will say later. Now, so that is kind of the main idea. Since mostly we are looking at a classification task, we have labels, we have data, so we, in theory, can just follow the standard recipe of supervised classification. But I just want to emphasize, like hypothesis generation, our main interest is the quality of hypothesis, not the accuracy. So I wanted to deviate from the standard presentation and start by showing you the hypothesis and some kind of other evaluation that I think is more about the quality of the hypothesis. So let's start with the example generated hypothesis. These are actually generated hypotheses from our system on the AI GC task that I just showed you. So you can see, maybe related to what the hypothesis earlier, AI generates much longer hypotheses in a way from what I did. And the first one is AI generated text tend to use more elaborate and descriptive language, including adjectives and adverbs to create a sense of atmosphere and immersion. Like this feels a little AI, but I don't know, it's actually helpful. And in general, this is like almost the most useful hypothesis. Like you can, if you go back, recall this example, this is what showed up in that example. Like AI is just a lot more descriptive than what typical humans would write. And the second one kind of matched what I came up with. AI also figured that human more likely to make grammatical errors, and human is more informal. And here, like we used another data set on deception detection. And for people who didn't know that data set, maybe this would come maybe a little hard to interpret. But still, just like maybe just read one of these, you can see is quite a high quality. At least like is probably better than the hypothesis that I can come up with by just looking at examples of deceptive text versus non-deceptive text. And now moving to more quantitative evaluation. So one thing that we did is that we think if this hypothesis is actually good hypothesis, they can actually help, not only help AI make good predictions. Like one possible is that we just made hypotheses that only AI can understand. AI can use it to make predictions, but they are meaningless to humans. So we show this to humans. And for these two tasks, we have humans do this task, detect which paragraph is written by human or not, a paragraph is written by human or AI. Then we have another group of people, we also show them these three hypotheses that I just showed you, literally just three. We generated more than three, but we decided like if we show you 20, it's hard for you to really do this study, so we just show you three. And with those three hypotheses, humans perform much better than they wouldn't have. Like in the AI-GC for tasks, I think the room distribution is actually close to this. The accuracy, the human accuracy was about 58. But if you see the hypothesis, if tell you those things that I just showed you, you will immediately become 73 on this task. And in deceptive review detection, the improvement is about 7%. And in addition, like both of these are statistically significant. In addition to this, like 100 of the participants find the hypothesis to be helpful. Like we have a survey question: did you find the hypothesis helpful? And over 40% of them found this very helpful or extremely helpful. And just to show you a little bit more of what's going on, right, between this literature only and hypogenic, I think I have time. So for example, like sometimes they just generate a very different hypothesis. Like this first one comes from literature. This is first person pronoun. Some other papers on this exact data set has discussed this phenomenon, but our system can come up with some new hypotheses that existing papers just never really touched on. And this other scenario is that sometimes they also kind of describe something very similar. And in this case, I kind of want to show you sometimes what a hyper-refine does. In general, hyper-refine tends to make the hypothesis longer. And it kind of integrated these two ways of presenting hypotheses. And sometimes it use examples to make it more descriptive. Sometimes it kind of add more theory around this, like similar to the AI-GC example, like it tries to explain why AI made it more descriptive. Although AI like doesn't necessarily have agency, it doesn't actually try to create an environment of immersion, but kind of this hypothesis try to add that part of theory around this very plain hypothesis. By the way, feel free to ask questions at any point if anything is unclear. Cool. That is the more qualitative part, or like the more about the quality of the hypothesis. I think that's less standard. Now we are going to move on something that's more standard. So we tried this on multiple data sets, 5 of them, and we can evaluate the performance. And to make the performance harder, we actually we generate a hypothesis from in-domain version or in-distribution version of the data set. Then we test it on the out of the distribution. For instance, like in AI-GC, we have 2 versions. One is the AI is GPT, and the other is AI is Llama. So we generate a hypothesis based on GPT AI's data, and then we use this hypothesis to decide whether something is written by Llama. So there's a level of like out of distribution that made it harder for this hypothesis to hold. And it requires the hypothesis to actually capture some phenomenon that is universal within that problem statement. And here, the performance is a big table, so I'm going to try to walk you through it quickly. So like few shot, which is kind of the in context, like I'm just going to show you a few examples without generating a hypothesis, and then ask you to make a prediction. Like in context learning, in some cases can actually do pretty well. Some, like for instance, in the Reddit data set, this one is about detecting depression. It can outperform zero shot by 11%. But in all data sets, if you use generated hypothesis first, like this work, if we use literature plus data, we get the best performance in all data sets. In some cases, the improvement is over 20%. And there actually this problem I didn't realize, like only by doing this, I thought I was very clever and found a new problem, but there's actually already a company called HyperWrite. Their entire thing is about generating hypotheses. I don't know how they make money, but we write on, maybe we didn't use it correctly anyway, or I want to give them some benefit of doubt, but they did pretty poorly on our data set. And if you have seen Notebook LM, like a new product from Google, is mostly not really designed for this purpose, but you can potentially use it for this purpose as well. It also did pretty poorly on our data set. And I was actually very surprised how bad they do. But I think it's actually useful to point out, in general, literature only just does pretty poorly. If you don't have any data support, only have literature, you cannot really excel in this task. And I think that is kind of one big limitation of this HyperWrite and Notebook LM. They are typically not really exposed to any data. They kind of take this assumption that LM is LM is AGI, so it can do anything. It doesn't need to see data. I guess clearly that's not true if you actually want to figure out some new phenomenon. One thing I do want to highlight is like this actual interesting bit. In most data sets in our work, literature will help a little bit. But in the case of AIGC detection, if we just use hyper-refined, it actually leads to a big degradation. Like in that case, like the literature just had too big an influence, and most papers on AIGC, they are actually mostly about building models to detect AI-generated content. So their description of the hypothesis or AI, what are the characteristics of AI is pretty bad. So if you use those too much, you will actually be biased, and as a result, you become unable to detect AIGC. So I guess like as a general lesson, I think the main idea is that if your existing literature is actually terrible, then you shouldn't use literature. And that can happen for certain classes of problems. And it really depends on the quality of research in that space, I guess. And we also, just to test this further, we also tried to take the generated hypothesis, say we use GPT-4 as the generation model. Usually in the big table that I just showed, we also use GPT-4 as the inference model. But we can also feed those hypotheses to a different model, Llama, and see whether Llama can use those to generate. And like, in fact, the version where we show this hypothesis to human, we are essentially treating human as another inference model. And in this case, we observe there is a small drop, but in some cases, it actually goes up a little bit. And the job is most substantial around AIGC. So in general, like Llama seems to generate like hypotheses that explains its own generated content that's very particular. Somehow GPT-4 doesn't interpret that as well, and vice versa. But overall, if we average everything, this also, despite the job, we still outperform the few shot baseline on average by 4%. So like even despite, if we show this hypothesis to a different AI model, there's some drop, but it still outperforms not generating a hypothesis at all. So that is kind of the major part of the first part. I guess I kind of want to end with a big claim. I do think AI will drive future hypothesis generation. I think this is a very kind of exciting place to work in. And I think not only us, I think like AI2 also had this discovery bench. This space is so wide open. Like although we are both in the space of hypothesis generation, but I think we approach it so differently. I think these are essentially two separate lines of work. But I think if you're interested, there are a lot of resources in this space that's coming up. And we have all our code and data available on Hugging Face and GitHub. Feel free to play with it. In fact, we welcome people to try it. And if you have a little bit of social science bent, and if you see, actually today in one of the meetings, I got like a great grammar induction is kind of a great example for this. Right? If you have some new data and you can try to ask the model to come up with grammar to explain a kind of unknown language or like a low resource language, I think that's actually a great use case of this. But if you have other kind of data that you think you have some data, you want to explain data with some kind of natural language based hypothesis, I think you can try to play with it. And I would love to feedback on how we can make this better. And we're also building a benchmark on this. So anyway, if you are interested in this, email me. Now, the second part, I'm going to quickly go through a different case where we are thinking about human AI decision making. We started to work on this before LLM, so this example doesn't have any LLM, but I think it still gives you kind of general philosophy of what's going on. So imagine you have a human and AI trying to team up, and in this case, you want a human to make the final decision, so AI is playing an assistance role, and we want to diagnose whether this person has pneumonia or not, given this chest X-ray or like any kind of lung-related disease. In this case, the human goals is humans achieving high accuracies. So it's very important that our main thing is want humans to do better. So we want AI to support humans. And this is true in many of these medical domains because I guess like at least most of our regulations, maybe our regulation will go away very soon. But anyway, most of our current regulation says that you cannot really just let AI make all the diagnostic decisions. So it's important to think about what kind of AI assistance can be helpful for humans. And we are going to focus only on explanations in this case. Like our assistants will only be explanations. And I'm going to start with a more theoretical argument. We have a entirely theoretical paper on this, but here I'm just going to illustrate the key intuitions. So the task that we are looking at is pneumonia diagnosis. And we consider two cases. One is the user, like the doctor, but I would need to use the word user because I'm going to introduce a bad user. Let's assume the user has no task-specific intuitions or has task-specific intuitions. That's just me explaining what no task-specific intuition means. It means that this person cannot really make sense of, it is an alien. It doesn't know anything about a human. It just comes from a different planet. It arrived at Earth, and then we force it to perform this chest X-ray diagnosis task. And I show you this image, and now I give you an explanation. The explanation are these red boxes. We tell you the AI uses this region to make a decision. And as an alien who knows nothing about this, what I'm seeing here is just a bunch of pixels. Maybe, I don't know, alien is not stupid. I'll give his benefit of doubt. It knows red boxes, so it can interpret the boxes. So I'm seeing a bunch of like red, black and white pixels, and then two red boxes. So that is entirely meaningless. So users cannot really make sense of these explanations, and his understanding of task decision boundary, or like his understanding of whether this person has pneumonia or not, is bounded by the model. Like there's just nothing that I can do other than following what the model is telling me, since I don't know anything about this. But instead, if we have a real doctor, then what's going on? It could be that I actually know where lungs are. And now seeing these two boxes, I know these two boxes are not on the lungs. So I can then use the explanations to verify the model is using valid information. And in this case, the model is not using valid information. Therefore, the model is more likely to be wrong. And if this mechanism actually holds, then we can hopefully get a human plus AI is better than AI. So it's important to highlight two things. First, my knowledge of lung location was not useful before I show you these two boxes. Like if I don't show you explanations, although I have this knowledge of where lungs are, but they cannot really help me interpret AI prediction. So there needs to be some synergy between your task-specific intuition and the explanation. And that allows you to leverage your task-specific intuition. And second, like it needs to be the case that this particular mechanism is correlated with model mistakes. Otherwise, like if the explanations are essentially random, even if I have this task-specific intuition, it won't be able to help human make a better decision. But at a high level, I kind of want to just convince you that task-specific human intuitions are necessary for explanations to provide value in AI-assisted decision-making. And this is kind of like, there are a couple of very related papers around the same time. For instance, like one of the papers make an even stronger argument saying that verifiability is the only way that a human and AI can work together and get a performance that's better than either human or AI alone. And there's some other more HCI thing. Our main difference is that we actually have a graphical framework, like based on graphical theory and causal theory to kind of justify this. But I don't have time to go into that in depth here. But now I'm going to show you this case on how we did a small thing on this, and we actually get a kind of pretty good performance from humans. So going back to this analogy first, in this case, our human goal is human AI decision making. And different from this, we are not just at the task level. We are really thinking about this, how AI and human fit together. And we want to make sure AI can plug in and fit these cases where humans have task-specific intuition that can allow AI to fit in together. Now, that is kind of our recipe for building human-centered explanations. First, we should articulate the mechanism of how humans can interact with explanations through these task-specific intuitions, and then we can generate explanations that tailor to this mechanism. So now go back to pneumonia. In this case, we are going to focus on a particular type of explanations, like say the explanation is AI predicts pneumonia. This is just the prediction label is not very helpful. So I'm going to show explanation. This explanation is in the form of image. I'm going to tell you this is why AI thinks this image is very similar to this example that also has pneumonia. Therefore, AI thinks this case is pneumonia. So there are two things for this mechanism, this explanation to work. First, one is that similar to the box example that I was showing earlier, the similarity between task example and justification is correlated with model error. Like if these two doesn't look similar, then the model is more likely to make a mistake. That correlation between model error needs to exist. The second thing that's what we are going to focus on is that similarity to AI is aligned with similarity to human. Like since we choose this explanation based on what AI thinks is similar. But what AI thinks is similar could be not the same as what a human thinks is similar. And as a result, it won't be useful for humans. So this is kind of visual example to show you what I mean here. Like for instance, this is a butterfly versus mouse example, which makes similarity much easier for a lay audience. This is our test image. And we use AI to find the nearest neighbor. This is based on ResNet. And I would say these two look nothing alike. And this is actually a real example. Admittedly, it's a little cherry-picked, but this is actually real two examples. These two are very similar based on AI, but they look very different from human eyes. But if we have a different way to think about a human perception, then we can find this image as the nearest neighbor within math. Well, actually, this is butterfly, within butterfly. And this at least visually looks a lot more similar to that, to my human eyes. So just to summarize, in this case, explanations are directly derived from AI representation. We are just looking for which one is most similar based on the embedding or whatever representation we have for this image. And the reason we are getting misaligned explanations is because the AI representation is not aligned. Like AI is asked to solve the problem of classification, but it may not solve the problem of aligned with humans' perception. So we want to learn human compatible representations so that AI is forced to use a image. Essentially, like if you are familiar with kernel, is essentially we want to force AI to use a similar kernel than humans, so that AI will generate a similar nearest neighbors that humans will also think are similar. Now, to do that, one big missing piece or one idea is that we are going to collect a lot of human triplet judgments. Like we have an example, we are going to get two references and ask human to judge which one is more similar to the original image. And we collected the first large-scale such triplet data set on chest X-rays. And then we can introduce this as additional loss in the typical classification framework. Now, our AI model not only needs to solve this decision task, which one is pneumonia or not, we also need to make sure that its model, its representation space is similar to human representation space. It can also predict which image is more similar to humans. So once we do this, then we have representations that are aligned with humans. Again, just to kind of just this more with this experimental design. So how we are going to show this is actually true. We have a test image. Now I'm going to show you two images. One is nearest neighbor in the predicted class. The other is nearest neighbor in the other class. So we call this neutral decision support. So now you can think of this as we have two sides of the argument, and we get AI to present the best argument for both sides. Then human judge which one is more similar to this test image and use that to determine the label. And if humans can make a good judgment, then it means that we are generating good quality explanations. And we consider two baselines. One is random, so we just pick a random image. And then we use AI. So these are not aligned AI, I guess. Unaligned AI that are not using a space that's aligned with human perception. And then we have AI with human compatible representations. So here are results. So one of the striking thing, of course, the fact I'm showing here kind of says that we are doing better than the other two. But one of the real striking thing is that AI by out of the box actually does worse than random. So somehow AI just completely ignore the human representations. It learned something that supports classification so well, but at the same time, humans cannot recognize it at all. And if you learn human compatible representations, then you achieve like almost a 20% boost over random, maybe close to 30% boost over the original AI representations. And this was very puzzling, like why would AI do that? So to make sure we didn't have any bugs, and also like this is actually a cool, like there are many reasons we designed this. So we also have another condition which we call persuasive decision support, and this one I wouldn't recommend to use in practice since it's essentially manipulating the doctor to choose what AI is going to predict. We choose the nearest neighbor in the predict class, but farthest neighbor in the other class. And in this case, the human task is the same. Just decide which one is more similar, and then use that to make a diagnosis. And in this case, we do see that AI performance gets much better. Like our performance is much better, and it gets close to 100% on butterfly and versus mouse. But AI now can actually outperform random in both cases, and outperform random non-trivially here on pneumonia. And this shows that AI indeed learned something in the representation. Like if you look at the farthest neighbor, like indeed the other class is pretty far from this class. So it did something that, like, if you are familiar with max margin, it did learn some kind of margin. It just is margin. On top of that margin, within one class, it didn't learn anything useful for humans, at least for this particular model in the task that we tried. And that is in some way justified because the model really has no motivation to use a space that's aligned with human perception. And solving this classification task is pretty simple. And I can already get a good margin between these two classes using a different representation. That like maybe they can use some pixels that humans do not use, and that reveals pattern, for instance. All right, so in the second example, we show that we get into the process a little more, and we show if we align them, we can better fit AI and human together and just allow human to make better decisions. So that is kind of the main picture of the day. This is the conclusion slide. Most of the idea is that it's useful to think about the idea of complementary AI is useful to think about how we can build AI to support human goals rather than build AI to just be human-alike. Like in general, that we also support human goals in some cases, but it's not guaranteed. And I don't think that's the best way of thinking about AI. And I think there are kind of three important components for this to happen. First, I think, and for all of this, I think there's a lot of work to work on. Like first, we need to have better understanding of human goals. And that's why I think this problem of specification is very interesting. Like how can we help human tell AI what goals they are trying to achieve? And hypothesis generation, we kind of introduce data as another piece of like specification that's not natural language. And what are the kind of possible ways that we can develop this protocol of explaining human goals to an AI agent or AI model? And then how do we understand the human capabilities? Like how do we figure out the shape of human here? Where does it reach? Is necessary for us to figure out where AI should jump in. And then we also need to understand the human-AI interaction. Similar to the second study, we need to figure out where the kinks are and how was the best way to get a human and AI to work together. And once we get a better understanding of those two, then we can think about how we should reshape AI with new objectives or new data sets and new algorithms. And if you're interested in any of these topics, feel free to email me. And I think there's a lot of interesting problems that require a lot of work from many different perspectives in this line, in this direction. Thank you very much. I'm happy to take more questions.
The last experiment that you presented, where like in the human AI complementary scenario results. And are you concluding there that this is due to like largely the human being able to read the AI explanation? I guess I'm asking because I wonder if you just like gave the human the king nearest neighbors images, if that would be enough, and you don't really need that whole up there. That's tricky.
Yeah, I guess the question is like, how do you get a k-nearest neighbor, right?
Oh, okay.
Right. Yeah, yes, indeed. This is a k. Like I think k nearest neighbor is still the most commonly used case-based explanation, right? Like, but how do you get k-nearest neighbor?
Okay.
Right. Yeah, exactly. Right. Like, I think the most natural way is that you build an AI model, then you take the representation at the final layer. That's what we did. Then you find your k-nearest neighbor based on that representation. And what we are saying is that if you need to introduce a different objective, then that will lead to a better explanation outcome.
Yeah, that makes sense. I think I was understanding.
Yeah, exactly. It's about how you get a k-nearest neighbor. Since like if you don't have any representation, then like if you just get a pixel, that will be even. Like actually, that's a good way to think about. If I just get a k-nearest neighbor based on pixel values, I just straighten this image into a long array, then that's even less aligned with humans. You will essentially get a like garbage as nearest neighbor, and it won't have any utility. Maybe it will be actually close to random. I actually don't know. I've not tried that experiment, but that's a good thought experiment here. Yeah. Cool. Yeah.
I was kind of curious. So in your explanation, or kind of like the motivation behind this, so if you look at the nearest neighbors for butterflies and moths, what the human thinks is the closest, in AI things are different, and then in experiment you showed the second setting where you showed the nearest neighbor for the predicted class and the farthest neighbor for the other class. I'm curious if because the nearest neighbor is not necessarily that human intuitive, it seems to me that the farthest neighbor probably also is not necessarily that far. Or if you try to say, well, I show the farthest class for the farthest neighbor for the predicted class, and then the nearest neighbor for the non-predicted class.
Yeah, exactly right. That's the right intuition, right? I think if like I guess like okay, actually I should set up the reason I started with I think there are a couple of kind of conflicting objectives. That's why I'm presenting this way. So one, let's start with the fuzziest one. I think this one is easy to explain, right? If you learn anything that aligned with human perception, the fuzziest one in the other class, there's a background. The AI does pretty well. So you kind of want the AI to you want a human to follow AI predictions. So if your representation is aligned with the human perception, then if you choose nearest neighbor in this predicted class and the fuzziest neighbor in the other class, you should get a 100% accuracy. So that's what we are hoping to see. And indeed, we see that in butterfly with moths. So that kind of shows that we learned a good representation there. In pneumonia, is close to 90%. It's still better than the other settings. So it kind of shows that we learned a pretty good metric. And in almost all conditions, maybe only the random, since random doesn't have the fuzziest part. And in AI, you also see that it's better than the previous version. So that says that AI also learned something. It's just AI didn't learn something that's actually aligned with human very well. So I think most of the problem happens in the nearest one. Like the fuzziest one still is okay. It looks quite different from the current one. But the nearest one doesn't look that similar, so it still has a lot of noise. And as a result, people don't get perfect. And that gets to the second. This is really nuanced argument. That's why I didn't do. In the neutral one, I think it's actually, like we are kind of really lucky in our setup. I think there's actually no guarantee that you will always do better if you learn a very good representation. Like since if you learn a really good representation, your nearest one in the other class could also be better at fooling the doctor or the participant. Then as a result, then doctor's accuracy doesn't necessarily improve. But if you have a good margin, then maybe that will still happen. So I guess we are lucky that we are in that case. So we even see in this case, we still see a good accuracy improvement. But in this case, it's actually a little trickier. The accuracy is not necessarily 100%. And if the two classes are very close, it's possible that you only can get 50%. If there's really no margin between these two classes. Yeah. Cool. Yes.
The chat.
Oh, I can.
How hard it is to evaluate the AI generated hypothesis. It seems there's a broad spectrum of creativity involved. For example, some hypotheses might appear unconventional but still make sense, while others may be more straightforward.
Yeah, that's a great question. I think in general, evaluation is a very hard question. I forgot, like we actually end up doing another experiment where we also did another subjective evaluation of our hypothesis to evaluate novelty and the plausibility. I think in our case, because our goal is to explain a phenomenon, so we have this like almost close to classification kind of setup where you can judge the quality of a hypothesis based on its utility in prediction. And as a result, we actually did find that like HyperRide, one of these commercial tools that I was mentioning, was bad. But Notebook LM actually can generate novel hypotheses, but they just have bad predictive utility. Like in terms of novelty, they are actually slightly ahead of our method, but their plausibility is lower than ours, even by subjective judgment. And by objective measurement, they are just a lot worse. Like we already see that, and humans can also kind of see that. Like I think that's kind of the part of hypothesis generation. There are many different things going on. Like if you think about it, you can come up with very crazy ideas. They will be novel, but they are not going to work, and that's not necessarily good hypothesis. And there's kind of an interesting balance to strike. And we kind of choose a setting to start with that's relatively simple. But in harder problems, I think how to navigate that balance is pretty tricky. And in the very long run, you probably need to have more active data collection than our kind of setting where you have a static set of data where you go and that you can go through. And in that active setting, then like it's harder to think about the balance, and maybe some crazy hypothesis actually true. And if you collect the right data, you can kind of show that it would be a bigger finding than showing a more plausible one. Anyway, I do think that's a very good question, and I think is a very nice kind of problem to think about. And I don't have all the answers. Yeah.
So essentially each of these, let's say there's a positive finding where there is a true classification, you artificially make it a false, and you train the hypothesis generation again on that opposite data. Did you do any experiments sort of going the opposite direction, trying to make it?
Yeah, we haven't done that in this, but this is exactly something what we are doing now. We are trying to create a synthetic benchmark, and there we are going to try experiments to see whether the model, like I think the synthetic benchmark part of what is going to do is just serve as a benchmark and see whether, like since there is actually a follow-up, it's kind of amazing how nowadays how quickly people move. We only released this paper in October, but then there's a follow-up in November. Kind of their main story is to hypothesize that our examples are like the data-driven part is not that helpful. Most of the hypothesis generation is based on the prior of the large language models. And I think in practice, there will be some balance, like depends on how you set up the problem. Like if we did a small experiment, like again, this is a work in progress. You don't call me on this as a final result. But I think one of the most recent experiments is that we create a fake setting in admission. And the data is created in a way that is only students who get F will be admitted. And the models indeed could never come up with that hypothesis. Like we give them some student data, and the model is just very counterintuitive. Like the model we're too different from the model's prior knowledge to believe that students with F will be the criteria of admitting into a university. But at the same time, I think that particular setup is not ideal just because that's also just not a good hypothesis for most practical purposes. So we are thinking about we are also moving to like a different setup where social media, maybe like more individual preferences, then is more benign than you would expect the model to explore any possible hypothesis. Anyway, we are actively building a benchmark to test this different ability. Like this is really inductive reasoning task. Like we are just thinking about how you can test inductive reasoning in the context of like hypothesis generation. Yeah. Cool.
more questions?
Yeah, okay, we go with the two more questions. Yes, go ahead. Yeah. Yeah, that's a very good observation. That's very subtle. I think in my work, I use explanation more broadly. So like the later experiment setup. So in our actual paper, if you read it, there are actually a third experiment where we test the justification. So as justification, is one-sided. I'm just trying to justify this prediction. And explanation can be more broad, and this decision support that I showed in the slides, I also view them as explanations. So that's the subtle distinction I was trying to draw there. And we did explain that in the paper. So I kind of inherited that terminology. But good eye, it's great that you caught that. But it's very subtle, and that's how I was trying to kind of draw lines between a few different things. No.
So I'm all in favor of the overall goal of AI alignment. And there has been this long distinction between AI replacing humans versus AI empowering. Now, you had one little line that human plus AI is better than AI. And I think there are situations where it makes sense potentially to replace the human being. So if you would be invited to give a talk at the car companies and should they develop self-driving cars or should they develop cars with intelligent driver support systems? So if your equation human plus AI is better than AI, they should not develop self-driving cars.
Yeah, I think that's I think there are kind of different scale of this, right? I think for instance, in the second project here, it was kind of human plus AI, the actual experiment. But in the first experiment, is actually mostly AI automatically generating hypotheses. I think my personal vision of the world, ideally, I want the society as a whole is that a human plus AI is better than just human or just AI. And in the car example, I think different people have different visions, but I can see the argument that if we only have self-driving cars, collectively, we still have a better society. But I think that, anyway, I think people can kind of choose which world that they think is better. And I think it can go probably either way. And I do think all the self-driving cars, in the end, if they are selling them to users, they still support. Like even in driving, think of like you sometimes drive for joy, you sometimes drive for commuting, and you probably want to make the commuting part self-driving. But if you are kind of driving along a beach and or you are looking for speed, you probably want to have that control yourself rather than AI doing that completely. But anyway, yeah.
I think Alessandro wants to have the last word on self-driving cars.
After 10 years of self-driving cars and hundreds of years of providing put into the industry, 95% of the car manufacturers are now moving towards ADAS systems, which is support systems, so that puts it right. So there is in-house defense. There is a middle ground also in that space in terms of how to do it.
Well, my comment, I think, is a little bit that we have to analyze the questions in more detail. Yes. And these generalized hypotheses are dangerous. I mean, the people for self-driving car would say, we have data that self-driving car will reduce the accident rate by so many %. And that's a laudable goal. And I mean, we are not there yet, but the people who pursue this goal have good argumentation for pursuing this goal. And the human can be the dangerous element in there. It's not necessarily my argumentation, but it exists argumentation that human is the dangerous element in the long-term future of driving cars.
Humans very dangerous element. We need to thank our speaker, but you can take this conversation, continue your time with me.
Thanks.